Hello everyone. So in today's class we will talk about a very small concept. It's called the resonance in LCR circuit. So in the previous class we have talked about a series LCR circuit, and the circuit was more or less look like this. So for example, we have a resistance over here, then that is connected to a capacitor. On the other side we have got a voltage source, which is alternating voltage source of course, and we have got an inductor connected to this circuit. So this is R, C and L. This is V. Now we know since this is an alternating voltage source, so we must write V to be is equal to V max sine of omega t. So in this case, in the previous class itself, I called that this V or the voltage source is a driver, and this drives the circuit. So basically what we got a differential equation which is of damped driven case. So in a sense we got an equation in terms of charges as L d2q upon dt2 plus R dq upon dt plus q by c, that's to be is equal to V, basically V, so which I am going to write as Vm sine of omega t. So we solve this equation, differential equation, using a trial solution which is q to be equal to qm sine of omega t plus theta, and finally we achieved at certain equation for the current, where we got the current to be given by I is equal to Vim cos of omega t plus theta. But what interests us is this Im, the maximum value of the current, which is basically given by Im to be equal to Vm upon something which is known as the impedance Z, and that impedance itself is written as Vm divided by square root of R square plus Xc minus XL whole square. Now Xc minus XL are what? Xc is the capacitive reactance and XL is the inductive reactance. So in short we write it as 1 by omega C, and this we write it as omega L. Now let's come to understanding of this particular circuit. Now this is a damped driven kind of a circuit. Now in a damped driven kind of a circuit, we know that there are two frequencies. One is the natural frequency of oscillation of the circuit, another is the driver frequency. And from our mechanical analogy, we can definitely come to a conclusion that whenever this damping frequency or the frequency of the circuit basically, that becomes equal to the driven frequency, in that case the oscillation becomes maximum. So in case of a mechanical thing, the amplitude of the mechanical vibration or mechanical oscillation become a maximum. Now in this case, since this is an electrical circuit, naturally we will expect the current in the circuit to be maximum. So whenever the two frequencies match, what are those two frequencies? One is the natural frequency of oscillation of the circuit, and the driver frequency, that means frequency of oscillation of the voltage source, which is omega as given here. These two frequencies, whenever they match or tend to match, in that case the current in the circuit becomes maximum. So for an LCR series circuit which is driven by the voltage source at frequency omega, for that we have found the current expression to be this, and at resonance we will now see what happens actually and what is actually the condition of resonance. So once again I will write the current expression I max, which is equal to V max upon square root of R square plus Xc minus XL whole square. Now the particular frequency at which this resonance occurs, let us coin that particular frequency to be omega naught. And in case of a series LCR circuit, the at resonance, that means at the frequency omega naught, the capacitive reactance becomes exactly equal to the inductive reactance. So we can write it as 1 by omega naught C, because that is what is the capacitive reactance, and omega, if it is equal to omega naught at resonance, because at resonance both the frequencies have to be the same, so that is why I'm writing it as 1 upon omega naught C, and that should be equal to omega naught L. So in a sense I can write omega naught square to be equal to 1 upon LC, or I can also write omega naught to be equal to 1 upon square root of LC. Now in the case of a linear frequency, now this is something that we have to remember, and more than that, in terms of linear frequency we know that twice pi f naught is equal to 1 upon square root of LC. So that implies f naught, which is a linear frequency, that's going to give you twice pi square root of LC. This is something that already we have known in our higher secondary classes. This is very well taught to us. Well, so in this case we will not talk in terms of the linear frequency, but we will rather concentrate on omega naught. All right. Now what actually happens to the total impedance? Total impedance is given by square root of R square plus XC minus XL whole square. Now since at resonance XE becomes equal to XL, therefore Z is nothing but equal to square root of R square, so which is equal to R. That implies we can write I max to be equal to V max divided by R. Now this is exactly same as that of a resistive circuit, because you remember whenever we were talking about the resistive circuit we got the current maximum to be equal to V max upon R. So in this case what is happening? In this case the capacitive reactance and the inductive reactance, they are somehow getting balanced, and we do not get any resistance from the capacitor and the inductor, so we remain with only the resistor. So that is why this is a term which is the maximum of the maximum current. I max or I suffix m itself is the maximum current, but we come across the conclusion that this I max varies with omega, that means the frequency. So as the frequency or the applied frequency is varied, at certain value of the applied frequency, when it becomes equal to the natural frequency of oscillation of the circuit, the current in the circuit shoots up to the maximum. That means the maximum current becomes even more maximum. So that then in that case we say that the current the resonance condition in the series LCR circuit has occurred. So if I have to plot this, then in a sense we can plot it like this. So for example, this is the Imax, which is varying with the frequency of the applied source. In that case we will get a graph which is like this. So this is the value, say at omega equal to omega naught, for which the current has reached a maximum level. So this is a value of the current which is the maximum of the maximum current. This, remember, this is the maximum current. I is equal to I max cosine of some omega t plus theta. So Im is nothing but the maximum current or the amplitude of the current. But the amplitude of the current is also varying with omega, the applied frequency. So when omega is changed from say 0 to some value of omega, now in that case somewhere in the middle we get a value where the omega or the applied frequency becomes equal to the natural frequency of oscillation of the circuit, and there the maximum current itself shoots up, and that is the condition of resonance in the circuit. All right. So many a times questions are asked in this fashion, that suppose in a circuit, let's say in a particular circuit we are given two values. Say for example, L has been applied to be 1 millihenry, capacitor C has been considered to be 1 nanofarad, and let's say R is given to be 100 ohm. for a particular circuit. In that case, what will be the uh, resonant frequency? Many a times this question is asked. So resonance frequency omega naught is nothing but 1 upon square root of LC. So that we can get very easily, square root of 10 to the power minus 3, because this is in millihenry which you have to convert into Henry. You will get 10 to the power minus 3 Henry multiplied by 10 to the power minus 9 Farad, because this is a nanofarad, so this will be 10 to the power minus 9 Farad. Now this is going to give us square root of 10 to the power minus 12, or square root of 10, once the square root is taken off, it is becoming 10 to the power minus 6. So we take it up, this much radian per second is my frequency, and now this is the resonant frequency. So this is the frequency which we have to hunt. So if you vary now the omega from some 0 megahertz to say 10 megahertz, then exactly at 1 megahertz, which is equal to 10 to the power 6, all right, the resonant frequency will be there. So at this particular frequency, current will shoot up to the maximum. All right. Now, why this condition is actually required? Now, resonance circuits have a variety of applications. For example, in the tuning mechanism of a radio or a TV set, this condition or this particular uh, situation is very important. Now, you might have seen that we have lot of channels distributed. For example, if we talk about the radio, now whenever we turn on the radio, we tune the frequency. Now, what is the meaning of tuning frequency? The exact meaning of tuning frequency is that inside the radio we have got a variable capacitor and let's say fixed inductor. Now once you tune it, that means you change the value of the capacitance and you change the value of the omega naught. That means the resonant frequency. Now if that particular frequency matches up with the frequency at which one particular channel is transmitting, in that case we get that channel. Alright. Similarly, in the case of a TV also, tuning the TV or setting a particular channel means to cause a resonant condition of the frequency. Alright. So the antenna of a radio accepts signal from many broadcasting stations actually. The signals picked up in the antenna act as a source in the tuning circuit of the radio. So the circuit can be driven at many frequencies. All right, but to hear one particular radio station, we tune the radio, and in tuning we vary the capacitance of a capacitor of the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. And when this happens, the amplitude of the current in the frequency of the signal, amplitude of the current at that particular frequency of the signal for that particular radio station is maximum, and we say the channel has been tuned properly. All right. Now this is all about the resonance condition in series LCR circuit. However, there is one more concept that is called the sharpness of resonance. That means we achieve a resonance, but how sharp it is. For example, do we have only a narrow distribution about omega naught wherever the resonance condition occur, or the resonance condition almost tend to occur for a broader distribution of the omega naught? That is something defines the term called the sharpness of resonance. All right, so that we will take up in the next class. So thank you for today.